So what are Artin's conjectures? Let's begin with the most basic of questions. In the 1920s, Artin made two conjectures that are still unsolved. They are in a way connected, and this talk is about the status of these conjectures almost 100 years later. The first conjecture is the primitive root conjecture, which I will explain soon, and is simpler to explain since the statement of the conjecture only involves high school level mathematics. The second conjecture needs more knowledge and involves Galois theory, representation theory, algebraic and analytic number theory, as well as group theory. So that will take a little bit of stress on the part of the listener, but I will try to keep it as self-contained as possible. So the second conjecture will require some background. Don't worry if you don't understand all of it. The motivation of the second conjecture is actually the motivation behind the Langlands program, as Professor Arthur would certainly testify to that fact. So the Artin's primitive root conjecture, the high school version, let me try to, hopefully there are some high school students here, but if not, that's fine. Let P be a prime number and consider the fraction 1 over P and write that down in decimal form. And by the division algorithm, it's easy to see that the decimal expansion is a periodic decimal expansion. And the period, that means the period with which the decimal expansion repeats, that's called a period. And it'll have to divide P minus 1 for elementary reasons from Maslow's theorem, actually. And it turns out that the period of the decimal expansion is actually the order of 10 modulo P. That's a little elementary number theory exercise. And so the question then is whether the order can be as large as possible, which is P minus 1. And this is essentially Artin's conjecture. So F equals P minus 1 if and only if 10 generates the residue classes mod P. That's a fact. And so the natural question is if there are infinitely many primes P such that 10 is actually a primitive root, so that the period is the largest possible period it can be. Now, let's give a few examples. Let's take P equals 7, and you write down 1 over P, and it turns out it has a periodic expansion of 6. So it's the largest possible it can be, and so 1 over 7 does satisfy that. By contrast, 1 over 11 has a periodic expansion of 2, and so it has a period length of 2. And that's because 10 has order 2 mod 11, because 10 is the same as minus 1 mod 11, and 11 minus 1 squared is, so get that. So generally, if I write 1 over P in base B, the period of the b-adic expansion will be P minus 1 if and only if B is a generator of the non-zero residue classes mod P. So the largest possible period that you can get happens if and only if B is a primitive root or a generator. That's the same thing as a primitive root, modulo P. And the question natural, are there infinitely many such primes? And this is Artin's primitive root conjecture that there are infinitely many such primes. So this is version 1. If B is bigger than 1 and not a perfect square, then there are infinitely many primes P such that B generates the coprime residue classes mod P. Note that a perfect square can never be a primitive root because it already is a square, and so it can only at most generate a subgroup of index 2, so it can't possibly be that. So that has to be ruled out. Now, such a conjecture is nascent in Gauss's Disquisitiones Arithmeticae. Oh, so it's not mathematics, it's arithmetic. Sorry, I made a mistake. Written in 1801, where Gauss seems to suggest that this is true for B equals 10. Gauss doesn't actually make an explicit conjecture, but he's kind of dancing around it. The first person to write a formal conjecture is Artin. And the date on which Artin formulated his famous conjecture is September 27, 1927, because this was apparently recorded in Hasse's diary. It was such a grand conjecture that Hasse recorded in his diary. The story of Hasse and the Artin conjecture is another story for another day. I won't be able to get to it, but I will certainly flash this picture so that you see Artin and Hasse. And this goes back to 1927. Now, so that's the high school version of the Artin primitive root conjecture I just gave you. Okay, so a second version is a little bit more precise. In this version, you're actually going to guess how many primes there are up to x that satisfy this problem. Not just infinitely many, but you're going to try to guess an asymptotic formula of this property. So how would you do this? So Artin arrives at this formula based on heuristic reasoning and elementary probability. And so how does that go? Well, B is a primitive root mod P if and only if B does not have smaller order. The order, whatever order it may have, it has to divide P minus 1. So you have to check that B to the P minus 1 over Q is not 1 for every prime divisor Q. So this is what you have to check. And by Dirichlet's theorem on primes and arithmetic progressions, the probability that Q divides P minus 1 is 1 over 5Q, where phi is the Euler-Toshin function. And by Euler's criterion, you can show that B to the P minus 1 over Q is 1 if and only if the polynomial x to the Q minus B has a root modulo P. And the probability of this second event happening is 1 over Q. So the probability of the first event is 1 over 5Q, which is Q minus 1. And the probability of the second event is happening is 1 over Q. And assuming these two events are independent, the probability of both of them happening is 1 over Q, Q minus 1. And therefore, the probability of it not happening for every prime Q should be the product over all the 1 minus 1 over Q, Q minus 1. So this is Artin's heuristic reasoning. It's not rigorous, of course. The density of primes for which B should be a primitive root modulo P should be something like this. Now, there are some problems with this reasoning, which I will not get into. Some of these problems were spotted by D.H. Lamer. It has to do with the fact that B could have powers of some number sitting inside it, and that messes up the density. But in general, if B is a square-free number, this reasoning is right, at least conjecturally at the moment. So this is the second version. It actually is predicting not only are there infinitely many, but there are a positive proportion of such primes. So this naturally raises the question, when does a polynomial have a root modulo P? I give you a polynomial, I ask you, when does it have a root mod P? Can you tell me a simple rule? Well, this is essentially algebraic number theory. The answer to this question is algebraic number theory. So from the previous discussion, we need to understand x to the Q minus B, whether that has a root or not. But generally now we can give any irreducible polynomial f of x, you'd like to know when does it have a root modulo P. And so if you let n sub f of P be the number of solutions of f of x equals 0 modulo P, then a high school version of the prime ideal theorem is just simply that the average value n sub f of P as you vary over the primes is averages x over log x. That will be some naive version of what's called the prime ideal theorem. This could be explained to a high school student. But the proof of this theorem requires algebraic number theory. This is what is the seductive appeal of number theory. You can pose very elementary problems that high school students can understand, but to understand the solution, and some of these problems are still open, like this one, the primitive root problem, requires a lot of machinery, a lot of conceptual mathematics. So that's a fascinating one. So it may help to review the prime number theorem and the classical theorem of Dirichlet to understand this more general prime ideal theorem. So the first person who made a serious attempt as to try and understand distribution of prime numbers is Gauss. As a teenager, apparently, when he was 15 years old, he made these conjectures. If pi of x is the number of primes up to x, then Gauss conjectured that the number of primes should be like the logarithmic integral. And if you integrate that by parts, the first term is x over log x. But there's a reason why you would consider the logarithmic integral rather than x over log x, simply because of what's called the theory of error terms, which I won't go into, but they are important in this conjecture. So pi of x is asymptotic to x over log x has been called the prime number theorem. It was conjectured by Gauss, but it was almost 100 years later it was proved formally. So 1793 was when the conjecture was made. 1896 was when it was finally proved. And in the intervening time, people were wondering about what is this problem. Chebyshev in particular was thinking about it. And he showed that there were constants A and B such that pi of x grows like x over log, but he could actually prove that it's asymptotic to it. And then he came up with this crazy theorem, which is even to this day rather mystical. He says if the limit exists, if pi of x divided by x over log x limit exists, it actually has to be 1. And so he felt that he was very close. So all he had to do was to show that the limit exists. But again, seductive appeal of these problems in number theory, that is really at the heart of the problem. That in order to show that the limit exists, you needed to create a whole branch of mathematics called complex analysis, which we now teach to graduate students. All right, so it has to do with the theory of the zeta function. So Euler was the first person to start thinking about the zeta function a century before Riemann. He studied it. He derived even what we can call a functional equation, but he didn't study it as a function of a complex variable. And that's what Riemann had done. Riemann had realized that the function zeta s equals summation 1 over n to the s has to be studied as a function of a complex variable. And Euler began with the observation that this Dirichlet series, the summation 1 over n to the s, can be written as an Euler product, what we now call a product, infinite product over primes. And this equality, that this infinite sum is the same as an infinite product, is equivalent to the unique factorization theorem. So with this particular equation, we have an analytic expression of the unique factorization theorem. And then he showed that by taking the limit as s goes to 1, you can deduce that there are infinitely many primes. So here he's redoing what Euclid had done in a far more elementary method, showing infinitude of primes, but in a much more complicated way, using the zeta function. And many times, even graduate students, my colleagues sometimes ask me, "Oh, what's the point of reproving something that you already know?" Well, here's a good reason. The reason is it opens the doors for finding new things. So Euclid's high school proof doesn't work for primes and progressions. And it's not going to work for answering that question of when does a polynomial have a root mod p? It just doesn't. You need to know algebraic number theory. So you need to know and the theory of zeta function somehow. So this idea of this method that Euler had used to show infinitude of primes was used by Dirichlet in his proof of infinitude of primes in arithmetic progressions. As a matter of fact, Euler studied the zeta function just as a function of a real variable. He proved some very beautiful things like this one that everyone I think knows. It's called the solution to the Basel problem, sum of the reciprocals of the squares. And in general, he managed to show for even values, zeta 2k can be written as a power of pi to the 2k. And as some of you may know, zeta 3, zeta 5, and all these things are still unknown, whether they're transcendental numbers or not, and whether they have anything to do with pi or not. Okay. So Riemann and the zeta function. So Riemann wrote an 8-page paper in 1859 on how the zeta function can be used to prove the prime number theorem. And in this paper, he was emphasizing the fact that it has to be studied as a function of a complex variable. He established analytic continuation and functional equation relating the value to s and 1 minus s. And he even gave an explicit formula relating the number of primes up to x and connected them with the zeros of the zeta function. Finally, in 1896, Hadamard, de la Valle, Poussin gave a rigorous treatment of Riemann's method and proved the prime number theorem basically by showing that the zeta function has no zeros on the line real s equals 1. Now, the location of the zeros of the zeta function is Hadamard and de la Valle, Poussin. The location of the zeros of the Riemann zeta function is a major unsolved problem. To this day, it's still, this is the famous Riemann hypothesis, that there are no zeros away from the line real s equals a half. If you had this knowledge, you can prove wonderful things. So we don't know it for the Riemann zeta function. We don't know it for a host of other functions as well. And this fact is going to figure in this question about the Artin conjectures, both of them. I haven't stated the second conjecture yet. It's coming. But the Artin primitive root conjecture is intimately tied up with the Riemann hypothesis, which I will try to explain. Now, in all of this approach to analytic questions, a useful tool is what's called a Wiener-Ikehara-Tauberian theorem, which is streamlined. So the complicated methods of Hadamard, de la Vallée-Poussin, and all these subsequent people were streamlined finally by Wiener and Ikehara in the 1930s. And the theorem is very, very simple to state. Let me just state it. I kind of gave a simpler version of the whole mess with my former student Aksha Watwani and her student Jagannath Sahu. And the theorem is the following. If you have a Dirichlet series, G of S, summation B of T over T to the S, and if you can factor out a Riemann zeta function out, kth power of the zeta function out, and the other factor that remains is G of S is a Dirichlet series which is absolutely convergent for real S bigger than or equal to 1, then immediately you can write down an asymptotic formula for the sum of B of T, T less than X in terms of this knowledge. It's a very useful thing to have. If we apply this Tauberian theorem to the logarithmic derivative, so when I take the logarithmic derivative of the zeta function, then I get this von Mangold function, which is defined as log p if n is a prime power and 0 otherwise. So I could write it essentially to weight the primes with weight 1 is not a great way to analyze the problem. It's easier to weight the prime p with log p, it turns out, because of this beautiful connection with the zeta function. And once you have that weightage, it's a trivial matter to undo the weights and then get an asymptotic formula of pi of x. But when you do that, it turns out that you can write down the prime number theorem in the form that psi of x, the sum function of lambda of n, is asymptotic to x. So the pi of x being asymptotic to x over log x is the same as psi of x, this sum lambda of n being asymptotic to x. So, and then a simple partial summation argument gives you pi of x is asymptotic to x over log x. So what am I trying to say here? I'm trying to say that the classical conjecture of Gauss opened the door for a new method in analytic number theory, that anytime you want to study something about the distribution of primes, there's probably a zeta function like object you have to set up and then provide analytic continuation to that object, and then apply the Tauberian theorem, and then you solve your problem. This is kind of a general methodology. And this, let me illustrate that methodology with primes in arithmetic progression. So this is Dirichlet. He had proved that there are infinitely many primes in arithmetic progression much earlier, but he never got an asymptotic formula. He only proved infinitely many. So there are two problems here. Infinitely many type problems, and then getting an asymptotic formula. The asymptotic formula is harder work because you have to get some sort of zeta function that you have to study. But the infinitely many may be easier. And in this case, Dirichlet had success in showing that there are infinitely many primes in arithmetic progressions just by using group characters. In fact, the study of character theory, which is a chapter in group theory, originates with Dirichlet and this problem, trying to understand primes in arithmetic progressions. So these are, if you take a character, multiplicative homomorphism of the coprime residue classes mod M, and then you attach a Dirichlet series to it. And just like the zeta function, there's an infinite product over primes because of the multiplicative property. And Dirichlet discovered these orthogonality relations, so which we now teach as part of a basic course in group theory. But the motivation for this discovery was the problem of trying to understand primes in arithmetic progressions. So using that, you can now apply, I'm going to just flash this very quickly. You can now apply the Tauberian machine. Now that I've set up the Dirichlet series, you apply the Tauberian machine, and then you get the asymptotic formula. And again, the punchline is the Dirichlet L functions don't vanish on the line real S equals 1. So there are no zeros on the line real S equals 1. And again, you have the analog of the Riemann hypothesis for Dirichlet L series, that namely all the non-trivial zeros of the zeta of the Dirichlet L function should lie on the line real S equals a half. So the proof that LS chi is not 0 for real S is harder, and the simplest proof requires actually the study of the Dedekind zeta function. So now I want to move from the Riemann zeta function to the Dedekind zeta function. So what is that? Well, here's Richard Dedekind. If I have an algebraic number field, and OK is a ring of integers, that is all the elements in that field that satisfy a monic polynomial integer with integer coefficients, the roots of that, then you look at that forms a ring, and it turns out that every ideal in that ring can be factored as a product of prime ideals. And so this is the unique factorization theorem of natural numbers now in the realm of ideals. And so just like the Riemann zeta function case, you look at the Dedekind zeta function, and you can factor it as an Euler product because of every ideal is a product of prime ideals. Therefore, you have an Euler product again. And by copying the method of Hadamard and Delavalliere-Poussin, you can show that the Dedekind zeta function extends analytically to real S equals 1 and doesn't vanish there, and then apply the Tauberian machine, and lo and behold, you get the prime ideal theorem. So that's, I don't know of any other way of proving the prime ideal theorem, which I told you about. I give you a polynomial, irreducible polynomial, and ask you how often does it have a root mod p. To answer that question, I have no other way except through the Dedekind zeta function. No other way. And so this seems to be the root. So now, the analytic continuation in this game only needs to happen until the line real S equals 1. But the question of whether you can continue it analytically to the entire complex plane and whether it satisfies a functional equation was answered by Hecke in 1918, shortly before Artin made all these conjectures. So Hecke showed this, but he showed it in a rather complicated way using theta functions of several variables. My guess is that Hecke and Artin were, I think they shared a wall in the university. Artin had the office next door to Hecke, and they shared a wall. And my guess is Artin always thought that probably there's a much more Fourier analytic approach that has to be taken for the analytic continuation of the Dedekind zeta function. So somehow it's interesting. That's very interesting. So this must have been at the back of Artin's mind when he immigrated to the United States and then supervised Tate and the famous Tate's thesis. But we'll get there in a second. Tate's thesis is really a Fourier analytic proof of Hecke's 1918 theorem. So here's a case where Tate didn't prove anything new in his thesis, but it's a sensational thesis, nevertheless, right? Because conceptually, it's a big deal. It's a new viewpoint of a very classical approach. So this is, again, goes back to what I said. Euclid proved infinitely many primes, but Euler proved this in a seemingly much more complicated way, but it's a more conceptual way. So Hecke had already proved this thing in 1918, but Tate's thesis is 1950. But redoing something, but in a much more conceptually profound way, which generalizes, by the way, to the Langlands program. Okay, so in 1923, Artin introduced his non-abelian L series. There were generalizations of the Dedekind zeta function, the Riemann zeta function, and the Dirichlet L functions. All these are special cases of a much more beautiful object. So if you have a Galois extension of algebraic number fields with Galois group G, one can associate to each prime ideal a canonical conjugacy class called the Frobenius class. Okay. And given a representation rho of the Galois group, the Artin L series attached to this is essentially, don't worry about this P naught and S or whatever. it's essentially the determinant of 1 minus rho of xp, or xp should be frob p, small typo there. Xp should be frob p, p to the minus s inverse. So it looks like the Euler products that we had already looked at in the case of the Dedekind zeta function. So this is looking like the previous objects, except you have a matrix, rho of xp is a matrix. And so you're taking the determinant of this, taking the characteristic polynomial of that. Now, Artin conjectures that each of these L series extends to the entire complex plane and is entire if rho is irreducible and non-trivial. This conjecture is still open, but it has been shown to be true if rho is one-dimensional. Artin himself showed that. This is called Artin's reciprocity law. Langlands and Tunnel and Carré have shown that if rho is two-dimensional and solvable, it's true. So in that case, we know. And much of the Langlands program has been inspired by this particular conjecture. The Brouwer induction theorem came shortly after. Brouwer induction theorem says that any character of a finite group is an integer linear combination of inductions of one-dimensional characters. And so using this, one can show, and Brouwer did this, he showed that all Artin L series have a meromorphic continuation to the entire complex plane. So we now know that these non-abelian L functions have meromorphic continuation. So the question is, where are these poles? Now, because the Hecke L functions have been studied and they've been shown to be entire, the Artin L series, being quotients of various Hecke L functions, are analytic up to real S equals 1. Therefore, you can apply the Tauberian machine to deduce that the distribution of the Frobenius elements in these conjugacy classes, which would be a generalization of the Dirichlet theorem in primes and arithmetic progressions. So this is what's called the Chebotarev density theorem. So by the way, I should add the Artin conjecture that the L function, I'll come to it, this so-called strong Artin conjecture. I'll come to that maybe in a second. Anyway, the Chebotarev density theorem tells us that these Frobenius elements are uniformly distributed in the group as G varies. Oops, I think I have, okay, animation problem here. But so when you apply the Brouwer induction theorem, you can apply, along with class field theory, a beautiful theorem of Kumar, shows that the possible poles of the Artin L series are contained in the zeros of the Dedekind zeta function. So if the Riemann hypothesis for the Dedekind zeta function is true, it implies immediately that there are no poles for the Artin L series to the right of real S bigger than a half. So this connection is interesting, since in the function field case, the Artin holomorphic conjecture was proved by Weyl as a consequence of his theorem establishing the Riemann hypothesis for congruent zeta functions. So this particular theorem is interesting for the simple reason that there may be an intimate connection between the Artin holomorphic conjecture and the generalized Riemann hypothesis. Oh, that's how you looked when you proved that theorem. I dug that up. All right. Now, the non-vanishing of L functions provides the solution to concrete number theory problems. So let me kind of recapitulate what I was saying so far. If I want to study the distribution of prime numbers, I should go to the zeta world and prove that the Riemann zeta function doesn't vanish on the line real S equals 1. If I want to prove the distribution of prime numbers in arithmetic regressions, I have to go to the L function world and show that the L function doesn't vanish on the line real S equals 1. If I want to prove something about the distribution of prime ideals, I have to analyze the Dedekind zeta function and show it doesn't vanish on the line, and apply the Tauberian machine and get this result. And if I want to get distribution theorems for those conjugacy classes that Artin introduced, it's called Chebotarev density theorem, I have to go to the Artin L functions and show that they have analytic continuation, they don't vanish on the line 1, and deduce the theorem. And there are much more. I'm just going to keep the table short. So there are more. Each L function contains some sort of sacred secret about prime numbers. So what does the universe of L functions look like? And so this is, now I want to bring in the Artin L series and the Artin primitive root conjecture in that context. So remember, Artin's heuristic reasoning involved these fields, splitting fields of x to the q minus b. And he was trying to say, well, the probability that this thing happens is 1 over q minus 1. Well, that can be translated into the statement that the prime p does not split completely in these Kummer extensions, zeta q b to the 1 over q. And then you apply the Chebotarev density theorem, and the density that Artin was using, 1 over q minus 1, actually works. But then there's an error term, because you have to do this now for infinitely many of these q's. There's an error term that you have to keep track of, and you have to control. So you don't want this to happen. So it's kind of an inclusion-exclusion principle over a whole totality of fields. So this is what Hooley in 1967 managed to do. He kept track of those error terms. But in order to keep track of those error terms and to keep them under control, he had to assume the generalized Riemann hypothesis, so that the error terms are under control. If you assume the generalized Riemann hypothesis, and Artin's heuristic reasoning, perfectly valid. It's completely rigorous. That probabilistic reasoning that Artin had used, completely rigorous, but you need the Riemann hypothesis to justify his heuristics. That's what basically Hooley's theorem is all about. Now, for unconditional theorems, myself and Rajiv Gupta in 1983 started this kind of program to show that there is a finite set of 13 numbers, one of which for Artin's primitive root conjecture is true. So we did this without the Riemann hypothesis, and our secret was sieve theory. Somehow, we still don't understand sieve theory. In many problems, sieve theory can be used as a substitute for the Riemann hypothesis. So we use the lower bound sieve as well as the Bombiri-Vinogradov theorem with exponent a half to derive this result. And this was the first unconditional theorem in this context. And shortly after, we refined this with Kumar, myself and Rajiv. We defined it to 7 numbers. And then finally, that's Kumar again. Finally, 7 was reduced to 3 by Heath Brown using improvements in the Bombiri-Vinogradov. Since after our work was done, Friedlander and Ivanich had managed to extend the range of the Bombiri-Vinogradov theorem with some weights up to 4 over 7. And that enabled Heath Brown to reduce our 7 to 3. So that's basically where it sits now. So in other words, if I gave you 3 mutually co-prime numbers, we now know that there are infinitely many primes p for which at least one of them is a primitive root. We don't know which one, but one of them is a primitive root. And in order to say that, this is all another approach, basically sieve theory, which is kind of interesting. Oh, that's Heath Brown. Okay. So these extensions, the Kummer extensions that show up are metacyclic. And so all these characters are monomial. And by known results, associated Artin L series are entire. In fact, we have what's called a strong Artin conjecture, which I'll talk about, which was proved by Professor Arthur and Clausel. For nilpotent groups, you have all the Artin L series not only are entire, but they are automorphic in the sense of Langlands, which I will try to explain. Now, the implication for the Artin holomorphic conjecture is underlined in a paper by myself, Kumar, and Sarada, where we show that if you had the Artin conjecture, in addition to the Riemann hypothesis, you actually can improve substantially error terms in these Chebotarev density theorems, which I underlined already as saying that control of the error terms allows to do this infinite exclusion-inclusion process over towers of fields. Okay. Now, what's the Langlands program? Okay, so, all right. In 1968, Langlands proposed a new program generalizing the work of Hecke. And in this context, he introduced what are now called automorphic L functions, LS pi, where pi is an automorphic, which we'll try to define shortly. He showed that all these L functions are entire, essentially, and satisfy a suitable functional equation, and predicted that Artin L series are among these. I mean, he didn't, his school, let's say, did it. I think for the Jacquet and Langlands did GL2, and Godban-Jacquet did GLN. So all these essentially are entire. So in other words, probably Artin's conjectures has been solved, but we don't know. If we only can show that the non-abelian L series is an automorphic L function, we're done. So in this way, Artin's conjecture would be proved via reciprocity law, namely that automorphic L functions, every Artin L function is an automorphic L function. This is the generalization of the work, building on the work of Gelfand, Fomin, Harshchandra. He viewed Langland's viewed modular forms from a representation theoretic perspective, and his innovation was to introduce an adelic approach and generalize the method of Tate's thesis to GLN. So this kind of adelic formulation is needed, and the assertion that an Artin L series is actually an automorphic L series is called the strong Artin conjecture. And as I mentioned, the famous Arthur-Clozel theorem says this is true for nilpotent extensions, and of which those Kummer extensions, I think, oh, they're not nilpotent, they're metacyclic, but anyway, yeah. So now the shift to the Adel ring is important because you have to understand the Adels from a larger perspective. Now, how do the Adels arise? Well, we all know that the rational numbers have the usual metric of absolute value, but there are all these p-adic metrics that we usually don't teach our undergraduate students, but probably we should. So you have a p-adic metric, one for each prime p, and this gives rise to the field of p-adic numbers, which are just as valid as the real numbers and complex numbers. And a famous theorem of Ostrowski says that these are the only way to metrize the rationals, either the p-adics or the classical one. And so looking at all these metrics on the rationals allows you to build this humongous ring called the Adel ring. So you're looking at all these completions at the same time. And analysis should not be confined to the real numbers or complex numbers. It should be done on a full scale with all these p-adic places in place. And so this vision of, I would think it's Artin, who inspired Tate's thesis, allows you to Fourier analyze L functions attached to the Adel ring and use the Fourier duality theorem as essentially the underlying concept that is responsible for functional equation, analytic continuation functional equation. So this we have a Haar measure on this ring, and Tate's thesis, the Fourier duality of this ring is at the heart of the functional equation of the Dedekind zeta function, and this formalism is now used central in the Langland's program. So this is why we should study, one of the reasons why we should study Adels. And the other reason we should study is, in some sense, if I asked you, what are all the possible characters of the rational number field? Well, it's answered by, well, they're all essentially Adels. Adels parameterize all the characters of the rational number field, modulo, of course, some trivial ones. So you have to mod out by Q. So the character group of the rationals is the Adel ring modulo Q. And this is Tate's thesis. It fits neatly into the Langland's program. And all the L series attached to the automorphic representations have been, as I mentioned, GLN L functions in the Langland's program have been continued to the entire plane. And we now know they have a functional equation. And in all cases, the coefficients of the associated Dirichlet series are multiplicative functions of a single variable. So in the time remaining, I want to allude to perhaps of the future of L series, future of Dirichlet series, and future automorphic L functions in this context by studying multiplicative functions of several variables. In some sense, if you look at Langland's Yale lectures on Euler products, he defined automorphic L functions via Euler products. So in some sense, you have a multiplicative function already to start with, associated to the L series of automorphic representation. So, but these are Dirichlet series, all of them are Dirichlet series of a single variable. And so maybe we should look at multiplicative functions of several variables. So before I do that, let me just point that another orthogonal approach to this whole business of analytic continuation and functional equation was presented by Selberg, who tried to formalize Dirichlet series in the most naive sort of way that we always have a Dirichlet series, we always have an Euler product, we have analytic continuation, functional equation, and just axiomatize these things, the properties that you've been using, just axiomatize them and call them this large class of Dirichlet series, which we now call the Silber class. And then he has basically said that this class of series has some properties there that you can identify. Some sort of unique factorization theorem should hold for this class of functions. In other words, he introduced the concept of a primitive function as being a Dirichlet series which is an element in this class, for which cannot be written as a product of two elements in the class with smaller degree. And that's what's called a primitive function. And he actually showed that every element in the class can be written as a product of primitive functions. So he showed that. And then he conjectured that this factorization is unique. We still don't know the proof of this conjecture. So he made these famous conjectures called the Silber conjectures now, that for primitive functions, you have some sort of asymptotic behavior of these sums and some sort of orthogonality principle between two distinct primitive functions. And in 1994, I showed that these Silber conjectures actually imply the strong Artin conjecture, which, I mean, the Selberg world doesn't say anything about automorphic L functions. But if you had the Selberg conjectures, you actually get the strong Artin conjecture. So probably Selberg conjectures lie beyond the realm of knowledge that we would identify in the Langlands program. So as I said, these are all L functions attached to a single complex variable. And so I want to use the remaining time to talk a little bit about functions of several variables. So multiplicative functions of several variables have been around for a while, but pinning down the definition of these things has been it took a while. Several people proposed the right generalization, but the right one, you know, as I said, conceptually right, seems to be the one that's been supplied by Vaidyanatha-Swamy in 1928. And he defined the following. Instead of considering natural numbers, you consider tuples of natural numbers. And then you say a tuple D divides a tuple N if it divides component-wise. So you set up a certain partial relation. And N over D would just simply be the corresponding Ni over Di. And then you generalize the Mobius function and you theory of arithmetical functions. So you can say, if I have f of n is summation d divides n g of d, you can invert using this generalized Mobius function. And so now that you have a concept of arithmetical function of several variables, you can define multiplicative function to be f of m1 n1 mk nk is just a product of m1 to mk, n1 to nk, provided the GCD of m1 to mk and n1 to nk is 1. So this was now there are plenty of people, if you look at the literature, plenty of people who have given generalized definitions of multiplicative functions of several variables, but this somehow seems to be the right one. I'll tell you why. Because the Dirichlet series of several complex variables that you associate to these multiplicative functions admits an Euler product. So an example is the famous Ramanujan sum. It's a function of two variables. You have a q and then you have an n. And if you fix one variable and you try to do the other, that's not a multiplicative function. That's not the way to define a multiple of several variables. So somehow this is the right way to do it. Several problems have emerged regarding Ramanujan sums, and this can be solved only using Dirichlet series of several variables. I'll describe two of them here. First one deals with these what are called higher convolutions of Ramanujan sums. And Ramanujan sums are very interesting from the standpoint of they seem to be objects that enable one to Fourier analyze an arithmetical function. So if I give you an arithmetical function, is there something like a Fourier series for an arithmetical function? And Ramanujan seems to have been the first person to have asked this question, and he came up with these things called the Ramanujan sums. And they have this orthogonality principle. And in 1932, Carmichael prove this orthogonality principle of Ramanujan sums. And this enables you to come up with a theory of what we would now call the Ramanujan Fourier expansions of arithmetical functions. So in joint work with Sneha Chobe and Shivani Goel, we started studying triple convolutions of these Ramanujan sums and proved some sort of orthogonality principles for triple convolutions. And then, of course, now the natural question is for these higher convolutions. And it turns out you really have to get your hands dirty and look at multiplicative functions of several variables. So in trying to understand these higher convolutions, recent work with Shivani Goel, we actually proved something a little bit stronger. So if you took multiple, how does this work? Is this light working? Yes, it's. So this multiple convolution here is actually a k-fold convolution. And the question is, methods of a single variable Dirichlet series are incapable of answering this question. And so you need to go to multivariable arithmetical functions and multivariable Dirichlet series. So we ended up actually evaluating this limit, and using this fact, we were able to answer a question about higher moments of Ramanujan sums, and that involves the asymptotic behavior of these higher moments, summation c cube n to the power k. And what we showed, so it's Shivani, what we showed is that the asymptotic behavior actually is something like yx to the k. The important factor is q of log x, where q is a polynomial of exact degree 2 to the k minus 2k minus 1. And to prove this, we needed to use a multivariable version of the Tauberian theory that I had outlined at the very beginning due to La Bretèche. This actually, the reason this theorem is important is because there was a paper by Robles and Roy in which they tried to analyze these higher moments, and it turns out that there's a mistake, serious mistake. The log term is completely missing, and in fact, there was a gaping hole. How did I get into this? Shivani first pointed out that she couldn't understand this theorem in this paper, and she kept bugging me about how to prove it. And then finally, we found out that it was actually a mistake in the paper, and that the naive method of single variable arithmetical functions simply will not work, and that somehow you needed to get into the higher dimension thing. So our paper corrects an error in a paper by Robles and Roy in which the log term is missing. So that's how I got into this, and I saw this is a very important theorem. So let me just flash the Tauberian theorem now of several variables. So you have a Dirichlet series of multiplicative function, sorry, it has to be a non-negative function of several variables, n1 to nk, absolutely convergent in various half planes, and I'm not going to get into the full details, but here are the technical, in case there are slides that are going to be made available so people can see the technical conditions. You need some sort of theorem about location of pole. It's not a pole anymore, it's a polar divisor. So there's a whole half plane of poles that can exist. So you have to worry about all these polar divisors. And then once you isolate all of these and know where these polar divisors exist, you can apply the Tauberian theorem in a neat sort of way. The summatory function of these several variables turns out to be given by x to certain power and log x to certain powers. And it all comes automatically once you set up the Dirichlet series. So that's a kind of the classical Tauberian theorem of Wiener in Ikehara has now been generalized to the multivariable setting by La Bretèche, and this is the form that we need. And when you, in our case, in the case that I talked about, the Ramanujan sums, the corresponding Dirichlet series factors as a product of Riemann zeta functions, and then you analyze the poles according to that theorem and end up getting the desired result. So concluding remarks. So coming back to Emil Artin, it's now nearly 100 years since Artin made his famous conjectures, and I hope I've convinced you that these conjectures are very interesting and very beautiful, and they are interconnected. And one of the conjectures is so simple that a high school student can understand it. The other conjecture is so complicated that nobody can. Well, it takes you into the Langlands program. So there's this kind of wide spectrum of remarkable mathematics. So they've inspired a century of developments in mathematics, especially in number theory, representation theory, general theory of automorphic forms. For example, I think most of you know Fermat's last theorem would not have been proved without the Langlands tunnel theorem, which is a first step in Wiles's proof. So beyond zeta functions and beyond these L series arising from representation theory, there seem to be other zeta functions of several variables that keep appearing. And it seems to me there may be a larger theory suggested by the examples presented in this talk. For instance, multiple zeta values have played an important role in our understanding of special values of classical zeta functions. And I'm trying to convince you that that's not the only esoteric application of multiple zeta functions, but there could be other applications as well that I've indicated with these moments of Ramanujan sums. So perhaps the next 100 years will see a development in this direction. So life is for discovery and self-discovery. There are higher levels to explore. May the Himalayan peaks inspire our minds to greater heights. So thank you for your attention.